Okay, hello everybody. Today, look, I'm actually sitting, so this is good. I'll give you an update as soon as I know, but I know that I'm probably going to need this video. So I'm going to teach you a little bit about polar and nonpolar molecules, and I'm going to review a little bit of Lewis structures. So just take a moment and fill out the notes as you go, and we'll see how you do. Okay. All right, so let's do this. Let's go here and let's go here. All right, so I'm trying to work okay. So I just want to make sure everybody understands that the most important part of this entire unit is being able to draw Lewis structures. So what we say in this unit is when in doubt, comma, draw it out. You know what I mean? So what that means is when you don't know what to do, normally if it's like a calculation, you find moles. If it's an equilibrium problem, you do a nice chart. And when it's a structure problem, you actually have to draw it out so you understand the structure. So typically when you do a Lewis structure, people do it different ways, but I think the easiest way to do it is to follow these steps. So first step is to count valence. And valence is just the group it's in on the periodic table. So when I look at this one, I'm going to say that Se has 6 valence electrons and O has 6 as well because they're in group 16. So this is looking like it has 24. Okay. Then you're going to pick the center atom. So the center atom is the least electronegative. It happens to be selenium here. So we're going to put selenium in the middle. Then you're going to bond everything. So what a bond is it's 2 electrons shared. Everybody likes that. And then you're going to give everybody an octet. So to give everybody an octet, you just put dots in. Everybody gets 8. And then you count. And if the number is 24, you're done. And that's all you have to do. But in this case, this is 26. If you count them all up, and you can trust me on it, it is 26. So what I know is I'm 2 over, so I'm going to need to draw an extra double bond. So I'm going to get my eraser out. Okay, so I'm going to go here and here. All right. Then I'll put my marker, and I'm going to put a double bond here. Now, is the double bond really here? No. This actually has 3 resonance structures. And so this is actually they get into this a little bit, but like a double bond has what we call a bond order of 2, a single bond is a bond order of 1. But this one, since it's an average of all 3, it has a bond order, or it's about a 1.33 bond. Okay, now you don't have to know too much more about that, but it's just just have to know basically it's that it's not really a double bond. It's shared between all of those. Okay, so I'm going to do another one. So again, when you do these, you should follow those steps each time. So when I do this one, I'm going to count them all up. This is 5. This is 7 times 3, so that's 26. So just like 24 has a look, 26 has a look. So it's going to end up looking like this, and I'm just going to do it a little bit faster just for the sake of this video. So we're going to give everything 8. And remember, when you're done, you count, and this does in fact have 26 electrons, so it's good. Okay, and we're going to do SO2, and so when you draw SO2, you bond it out. Okay, this is going to have, it's going to have 18. So what you're going to learn is that the numbers are going to tell you if there's a double bond or not. And so when I do this, you're going to find out that everybody has 8, because you always give everyone octets. If you don't like to draw octets, you can, draw the lines, which that bothers people, but whatever. And you're going to find out that when you count this out, it's 20. And anytime you're over, that means double bond. So what I'm going to do is I'm going to add another eraser here, and I'm going to put a double bond here. And this one happens to have resonance. So again, when you have resonance, you're supposed to draw out both resonance types, which that's a single bond with all those electrons present, double bond, boom, 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 one unshared pair. And so that is the correct structure for sulfur dioxide. All right, let's do the last one. So Si, S2. So we're going to put Si in the middle. I'm just going to jump to it right away since I memorized it. So it's going to look like this. This is exactly the same as CO2. And the way I know this is Si is like C, O is like S, and I just know that CO2 is always linear like this. And then understanding that when you draw it out, you have to draw resonance. Now, this comes from practice, so you can get the practice from reading the book. You can get the practice from doing the model lab. You can do the Pearsons. You get a little practice. It's not that bad once you get going on it. But again, biggest skill, can you draw Lewis structures? That's where it needs to start. Okay, so then after you draw Lewis structures, you need to be able to find the shape of this. So Vesper theory stands for valence shell electron pair repulsion model, where electrons hate each other. And they hate each other because they're both negative and they can't stand being close to other negative things. So that's basically it. So anyways, when you're doing this, you have to be able to look at it by counting domains. So a single bond, a double bond, a triple bond is one domain. Unshared pair, one domain. And then you just have to memorize that chart that I sent you. If you don't remember where to find the chart, it's right here. And you do have to know this one. So it's in, if I look under my lessons for the week, and I emailed it to everybody, and it'll be part of your quiz. So this is required that you memorize these shapes, okay? You have to know the shapes. You have to know the bond angles, at least 120, 109, and 180, 109.5. So those are the only ones you have to know. And basically, you mostly have to know the front. And then anything on the back, you just have to know like trigonal bipyramid and then octahedral. They don't make you know the extra shapes on there. All right, so we're going back to here. So when I look at the shapes of things, okay, so did I skip that? I must have skipped one. Oh, okay, I'm going to go here and I'll show you guys one to do. This is kind of a shape one that I want to kind of talk about with Vesper shape, since I have that one. So let me hit this and then hopefully it's here. Okay, so when I'm doing the Vesper shape here, so when I do the Vesper shape for these are already pre-drawn. Oftentimes this is how it works. It's already pre-drawn. I just count domains. And as you can see, let me get this back into presentation mode here so I can, all right, that's much better. Okay, so when I'm drawing the shapes here, people, do you see how this has 1, 2, 3, 4 domains? And that means it's tetrahedron domain. Okay, so that just means it has 4 domains. But this is bent in shape because 2 bonds, 2 bonded ones, right? 2 unshared pairs is bent. And when you have, this one actually has resonance where this double bond could be here or it could be here or here. So for this one, it has 3 domains and all are bonded. So this is trigonal planar. Okay, now if you get a big molecule, you just look at it in between. So for example, on this one right here, so I'm going to look at the N. So the N would have 3 bonded domains and 1 unshared pair. So 3 and 1, you look it up on your chart. It's right here. So when you look up 3 and 1, which I went to the wrong side, but I'll go back to it. 3 and 1 happens to be trigonal pyramid. And so this shape is trigonal pyramid, at least this guy right here is. And so is this. But the middle carbon, if you look, it has 3 bonds, all unshared. So you look it up, and it's 3 and 0, which is trigonal planar. This one is obviously linear, right? Because around this carbon, there's only 2 domains. And this one would be 1, 2, 3 with 1 unshared pair. That would be trigonal pyramid. So most of the time, they're like trigonal pyramid, planar, tetrahedral, that kind of stuff. If you look at this C, it has 4 domains, all bonded. So this would be tetrahedral. This is linear, right? Now, when you have a big molecule, you just look at one at each time. So this C right here would be trigonal planar. It has 1, 2, 3 domains all bonded. But this N would be pyramidal because it has 1, 2, 3 with 1 unshared pair. So when you look at them, you can look at the whole thing or you can look at part of it. Let's look down here. See this guy right here? So this has got lots of shapes. This has definitely got some linear going on here, right? This is some trigonal planar going on here. And this right here, since it has 2 and 2, is bent. So oftentimes if you have a big molecule, you just kind of divide it up and conquer. All right, so let's go back to this whole concept of polar, non-polar, which is where we're headed for today. So when things bond, what happens is they share, and sometimes they share mean. Okay, so this is that tug of war thing we did. I'm not sure which student I did it with, but we always do tug of war. And when they share electrons, if they share evenly, it's called a non-polar covalent bond. So this type of bond is when it's just perfectly even. They typically will give you what we call the electronegativity values, and you subtract them. And if it's less than 0.4, it's purely nonpolar. If it's greater than 0.4, but in this range, right, it's polar covalent. What polar covalent means is they share unevenly. And these have what we call dipole moment. Okay, so your book's going to talk about dipole moment a lot. And a dipole moment is, this is when the electrons, like one of the sides is more negative than the other. So in this case, if I have something like HCl, right? So Cl is not nice with electrons. It really likes them. So it pulls the electrons closer to itself. And poor hydrogen becomes slightly positive. And this is like the thing that causes like hydrogen bonding in water. This type of bonding is present when they don't share evenly. And then when the electronegativity difference is like greater than 2, or it's really large. So you don't have to memorize these numbers. These are given to you on a test or something. You just have to know like, hey, oh, they're about the same. They're going to share the same. Oh, they're different. They're going to share differently. But when electrons are given up and lost, it's ionic bonding. Okay. So that being said, let me move on. So the magnitude and direction of the bonding is going to determine whether or not the molecule is actually polar or nonpolar. So an interesting thing, I kind of want to talk about PI3. All right, so I'm going to draw it out again. We drew it earlier. So it's trigonal pyramid. And what I mean by that is it has, okay, so it has 3 bonded sites. This is the correct way of drawing it. We did it earlier. And what happens is there's an electronegativity difference between these atoms. And you can look it up. I'm just going to kind of draw it in. So they don't share evenly. And since they don't share evenly, what happens is this molecule has areas on it that are either negative or positive. Now, a good clue that we'll often talk about with this type of thing is we're looking for symmetry. So symmetry, I'm just going to write short symmetry. So symmetry is when the molecule is like perfectly balanced and all the dipoles cancel out. That's a nonpolar molecule. But if it's asymmetrical, if there's something on this molecule that makes it either negative or positive, like this unshared pair, then this is a polar molecule. And so what you have to do is you have to be able to look at something and determine if it's polar or nonpolar based off of its shape. So what can happen is, and I'm going to give you an example of CO2. So remember how I always said CO2 kind of looks like this. It is linear. It has a 180 degree bond. And what happens is the O's love electrons. So it tugs this way and these guys tug this way. But the dipoles completely cancel out. It's kind of like if you're playing tug of war and both of the sides are exactly even, nothing's going to happen. And so this is a non-polar molecule. Whereas water, if I draw water out, and it depends, you have to be careful how you draw it. Water is clearly bent, right? So this would be a polar molecule because it has a negative part right here. These electrons, these unshared pairs are negative, and then these don't share electrons evenly. So it has a positive part. So what you have to know is if it's symmetrical, it is nonpolar. If it's asymmetrical, it is polar. Okay. So keep that in mind as we go. So asymmetrical molecules, this is just more of the same, are, like CO2 versus H2O. So any molecule that has unshared pairs on it in the center atom is almost always polar. The one exception is like XeF4. So I'm going to draw this one out so I can show you. So every other time, like all the trigonal pyramids, all the bent ones are always polar. Okay, usually linear, tetrahedral, depends on if they're symmetrical. But anyways, so typically what happens, this one actually happens to be nonpolar. If the shape of the molecule is like everything cancels out and it's perfectly symmetrical, then it's nonpolar. But if you have like something that's asymmetrical, like SF4, okay, so I think this one, let's see, this would be, yeah, this one has 34 electrons in it. So I'm going to draw this one out. This is a classic example of a polar molecule. So this is expanded octet. So expanded octet occurs, so it has an unshared pair there. This is definitely polar now. So the difference between these two is this has perfect symmetry. This does not. Okay. So I'm just going to kind of move on. All right. So what you should be able to do is look at something and determine if it's polar or nonpolar. So I'm going to draw a really big one. I'm going to draw acetone. So here we go. So acetone, it looks like this. This is nail polish remover. Okay, these have it's almost saturated with H's, but it's not. It's not saturated completely. All right, and there's a couple unshared pairs here. And this would in fact be polar because this part is negative. And it's not super polar, like there's like certain things that are really polar, like ammonia is super polar, right? So here's ammonia's structure. So anything that has an unshared pair, when you draw it out, like on the center atom, this is pretty much always polar. And then something like, oh geez, let's just do SO2. So if I do SO2, the SO2 happens to have resonance. I just know what it looks like as I've drawn it a million times. And this one's bent, and this is definitely polar because this is asymmetrical. All right. So what is nonpolar? Well, methane, right? So if I draw methane has a bunch of H's all around it, and they're all the same. And since they're all the same, all the dipole moments cancel out. It is nonpolar. Okay. So when drawing and figuring out polarity, you double check your structure. When in doubt, draw it out and make sure that you understand how to do all the polar, nonpolar stuff. Okay, so I'm going to pause this video here. Let's